Hi, we're Team SS Larson, and today we're busting myth number 6.
Myth number 6 states that a force is needed to act on an object in order to keep the object moving at a constant speed.
There are many misconceptions about forces in motion, and this is one of the most popular.
Let's take a look at what most people think. Imagine a roller ball on an ice skating rink, a frictionless surface.
Yeah.
What would happen to the ball after I roll it? Is it A, gonna keep moving at a constant speed for a really long time, or B, gonna stop a little bit after rolling?
Personally, I think it'll stop because most of the time when you roll a ball, it'll stop. So that's my answer.
Okay. Do you think I would need to put a force on the ball to keep it moving at the same speed?
I think so. Like wind or something, because I don't think it'll go on its own forever.
Okay.
Without something making it.
The correct answer was A. The ball would keep on moving at a constant speed. Why were they wrong?
You were wrong because Newton's first law states an object in motion will stay in motion, and an object at rest will stay at rest due to inertia, unless an unbalanced force causes its velocity to change. Inertia is an object's resistance to change motion, and it depends on an object's mass. Our first argument against this myth number 6, is a short demonstration with Josue and a rolling chair. Let's check it out. What happened here in this example is that friction is the unbalanced force that causes Josue in the chair to accelerate or slow down in this case. In this occasion, Josue would need to apply force to the chair to keep the chair moving at a constant speed.
But according to Newton's first law, without unbalanced forces acting upon the chair, inertia would keep the chair in motion.
If the chair were to be in space, it would move on forever at the same speed, unless an unbalanced force is acted upon it.
The truth is that a force is only needed to make an object accelerate, not keep it in motion.
Our second argument against this myth is a free body diagram based off of the demonstration we just showed you with Josue in the rolling chair. Here's a free body diagram. Josue has F gravity acting on him because he is on Earth, and F normal because that's a support force, and F friction because of the movement between the wheels and the asphalt, and F applied because he pushed himself off the curb in order to get the chair rolling. So let's say we had these values for force. So let's say F normal was 30 newtons and F gravity is also 30 newtons. That means that in the y direction the net force is 0 because 30 newtons minus 30 newtons is 0 newtons, so these forces are balanced. However, in the x direction we have for F friction 40 newtons and for F applied 35 newtons. So in the x direction the net force is 5 newtons to the left, and so these forces are unbalanced because it's not 0 newtons. This is what F friction is what caused the chair to accelerate or slow down in this case.
This free body diagram relates to Newton's second law, which states all unbalanced forces cause an object to accelerate.
Also, according to Newton's second law, this way, if his mass decreased, then he in the chair would accelerate more because the equation force equals mass times acceleration says that if mass decreases and forces are kept the same, acceleration increases. Our third and final argument against this myth is an example from an online simulator called Rocket Sled on Physics Classroom. As you can see, friction is turned off and air drag is turned off. And you can see that his net force is 0 newtons, telling us that the forces are balanced, yet he's moving at a constant speed. So this once again shows that no forces are needed to keep him moving at a constant speed, and his speed is constant at 13.1 meters per second. So once again, forces are only needed to accelerate an object and not to keep them moving at a constant speed.
You have now seen myth number 6 busted.